Building a computer vision system from scratch traditionally requires massive datasets and months of continuous training. Modern developers bypass this by deploying models capable of recognizing complex visual patterns the moment they are initialized. The PyTorch Torch Vision library provides immediate access to a wide roster of open-source architectures. These models come packaged with pre-learned weights, meaning the mathematical heavy lifting has already been completed by global research teams. This walkthrough covers two critical phases of development. First, we will write the specific Python code required to run an image classifier. Second, we will analyze performance data to determine how to choose the right model for a specific hardware environment. A project will fail if the selected model architecture overwhelms the memory of the target device. Hardware-aware selection is as essential to a successful deployment as the Python code itself. Before implementing the code, we must understand the data foundation. These models learn to see by processing ImageNet, a massive database containing over 1.2 million photographs categorized into 1,000 distinct labels. This diagram represents a convolutional neural network architecture, specifically the legacy VGG16 model, which serves as our baseline for how data flows through a vision system. An image enters on the left and passes through a sequence of specific layers. The blue convolution and red max pooling layers systematically break down raw pixels into abstract features like edges and textures. Finally, the green fully connected layers distill those features into a single classification. Pre-learned weights are the optimized numerical values stored inside each of these layers. By importing the architecture with these weights already tuned, you eliminate months of computational training time. Understanding this architectural flow is a requirement before attempting to write declining code. Now we can move into the PyTorch implementation. Our primary task is to apply the lightweight MobileNet v3 small model to a single test image within the PyTorch environment. We will use this photograph for our test. The model must analyze these pixels and accurately identify the subject. Successful implementation depends on correct input shaping. The MobileNet v3 small architecture expects an input shape of 224 by 224 pixels across 3 color channels. We must apply PyTorch transforms to crop and resize the photograph into this exact tensor format to avoid a runtime error. Once the image is formatted, we create a data batch and pass it through the model. Finally, we decode the resulting probability scores into human-readable class names. In this instance, MobileNet v3 small identifies a giant panda with 99.96% probability. This demonstrates the efficiency of using pre-learned weights to solve complex vision tasks with minimal code. This bar chart compares the accuracy of various architectures. The blue bars show top 1 accuracy, where the model's primary guess is correct, while the red bars show top 5 accuracy, where the correct answer appears in the top 5 predictions. On the far right of the graph, EfficientNet B7 appears as the top performer across both accuracy metrics. This graph plots CPU inference time, the milliseconds required to process a single batch. This data reveals the performance bottleneck associated with high-accuracy models. EfficientNet B7 requires over 1,500 milliseconds per step on a CPU. In contrast, smaller models like EfficientNet B0 and MobileNet on the far left execute 10 times faster. Offloading inference to a GPU reduces processing time across the board. However, the chart shows that the largest models still face a significant speed penalty compared to their lightweight counterparts. For applications like autonomous driving or live video filters, a 1.5-second processing delay is disqualifying. Real-time response requirements often take priority. Physical model size is the final constraint. When deploying to edge devices like smartphones or embedded sensors, the memory footprint determines which models are viable. The legacy VGG19 model requires 549 megabytes of storage. Conversely, MobileNet v3 small is highly optimized, requiring only 10 megabytes of space. This bubble chart combines accuracy, processing speed, and file size into a single framework. The vertical axis tracks accuracy, the horizontal axis shows speed, and the bubble size represents the physical weight of the model file. The EfficientNet models near the top right provide high accuracy at the cost of speed and size. The MobileNet cluster on the left is purpose-built for mobile applications, prioritizing speed and a small memory footprint. No universal best model exists. Developers must calculate the correct compromise between file size, speed, and accuracy for their specific deployment environment. Running image classification in PyTorch is straightforward once the foundational concept of input shaping is understood. Developers must balance the implementation of the code with the physical limitations of the host hardware, from massive cloud servers to mobile devices. The resources below contain the link to the full Colab notebook. You can load your own images and swap the model names to experience the differences in speed and memory usage firsthand. Machine learning proficiency is defined by the ability to optimize pre-built architectures to function reliably within the strict constraints of real-world hardware.